Again, you want to open up your .res file. And the first thing we want to do, again, if we look at the I over sigma, here the I over sigma is 43.3. So this is very good quality data. The R int is about 3.5%, which is very good as well. Space group suggests P1 bar, which is one of the common space groups. So now we want to do an initial solve or do a solve to get our initial model. And if you're using SHELX, use SHELX-T as well. Now, one thing you might want to see here is you'll see our Z value is set to 4 and Z prime set to 2. What I would recommend is when you're doing this for the first time, just assume that there's one entity in the asymmetric unit. And if we assume that, then we need to change Z to 2 so that Z prime is 1. Because remember with P1 bar, there's only 2 symmetry operators, the identity and the inversion center. If you think P1 bar is not the correct space group, you can go to suggest space group and see what it suggests. It also suggests P1 bar as well, in addition to the non-central symmetric group P1. So we're going to stick with P1 bar. Now make sure you have, if you're using SHELX, use SHELX-T. It'll automatically auto assign atom types. So we click solve, we're going to get our initial model. So I purposely didn't give you a proposed structure for this because I want to walk you through some of the troubleshooting that may come up. So in this chemical formula, it's given us carbon, hydrogen, oxygen, and fluorine. So this is our initial structure model. So now I'm going to go to refine. Again, if you're using SHELX, we use SHELXL. It's always good practice to put the ACTA on. So we'll click ACTA. That way it creates your CIF file each time you refine. Number of cycles, however many you want. I like about 5 or 6, so that way it converges in a timely fashion. Peaks, you can set it to whatever you like. Most of our atoms are assigned. So now if we click refine, we get this. So right now we're about at 19.64% R1, 55% weighted R2. So let me refine again until our shift parameter converges. And so you notice here that the shift parameter is not converging. So this tells you that there's something not right about this model. So there's something that's unhappy in what we've done so far. And so if we want to see this manifest itself, what I like to do is let's go ahead and do anisotropic refinement. And when we do anisotropic refinement, if one of the atoms is the wrong atom type, either we'll see the thermal parameter go to negative, indicating that the atom type is too small for that particular position, or you may see the thermal parameter balloon become too big because it's too big for that atom site. So it's always good to do anisotropic refinement, and that'll kind of help manifest any type of wrong atom type you may have. So we did the anisotropic refinement, and one thing that I should definitely point out immediately is that you notice this fluorine on the benzene ring looks like a pyramid. And whenever you see something like this, this indicates that it is, we call it negative thermal parameters, which is a no-no. You can't have something with negative thermal parameters. You know, typically when this happens, this means usually that the atom type you have for that position is too small. So you want to try and increase it to a larger element because it has more electrons. It may occupy that position better. So one thing you may want to do is say, what element can we choose? Because obviously out of all the elements in our formula, fluorine is the heaviest one. So what we're going to do is, let's first check and see what the bond distance is of this carbon-fluorine bond. It's about 1.72 angstroms. Now let's go to this CF3 group and just get an idea of what a typical carbon-fluorine bond is. About 1.332. So obviously this bond length does suggest that this is not a fluorine atom because the bond distance is a lot bigger compared to the CF bond distance in the CF3 group, because that was about 1.33. So we need something bigger here, and it needs to be something that just needs a single bond with a carbon atom. So for example, it couldn't be, example, nitrogen, because nitrogen you would need like an NH2 group. It couldn't be phosphorus by itself, because a single bond phosphorus would have hydrogen atoms off of it. It couldn't be a sulfur atom, because even a sulfur atom, you would need a hydrogen atom off of that position. And if you look at this position, there's no Q peaks 1 angstrom away from this position to indicate a hydrogen atom may be there. And so basically this has to be a halogen, because halogens form single bonds with carbon. And if we go to the next heavier halogen than fluorine, it would be a chlorine. So if we right click on the fluorine, go to type, and then click more, a periodic table appears, and you can select any atom you want to fill that position. So I'm going to select chlorine. And again, the reason I did this is because off of this position, I don't see any Q peak about 1 angstrom off that would suggest that there's hydrogen atoms in that neighborhood. Now, if I change this to chlorine and I notice some Q peaks about 1 angstrom apart, maybe that would suggest it could be a sulfur, like an HS group, something like that. But for now, I'm going to call it as it is, call it a chlorine atom. And you can also Google a carbon-chlorine bond to see if the bond distance tabulated is close to the bond distance we see here. And that'll also help you confirm that this is, in fact, a chlorine atom. The second way you can confirm it is if by refining it, do we see a drop in the R factor? That means we went in a good direction of modeling this data better. So, I mean, it went from 55% or 50% to 32.5%. So obviously we went in the right direction. This was in fact the chlorine atom. And if you look around the chlorine atom, we don't see any heavy electron density peaks 1 angstrom off. And if you're saying, well, hey, maybe we don't have enough peaks, let's change it to 35, for example, and refine. And even at 35 electron density peaks, we still don't see any electron density peaks around the chlorine. So that's a good indication that this was, in fact, a chlorine atom. And also notice now that our shift parameter is converging. Before we had it as a fluorine, the shift wasn't converging because that fluorine atom wasn't doing a good job of modeling that electron density. So we've corrected that atom type because it had a negative thermal parameter. Now let's continue. So now we've checked the atom types. We've corrected some of the mislabeled atom types. We've done thermal ellipsoid or anisotropic refinement. So it's called anisotropic when you model with thermal ellipsoids. The next step would be to add hydrogen atoms. So again, to add hydrogen atoms, you can just simply click under the toolbox, add H, or you can go to Tools, click on hydrogen atoms, click add hydrogens. Now the other options are if you just want to add hydrogens to one particular atom. For example, if it's a aromatic carbon you want to add a hydrogen to, you can just click on this and you can individually add hydrogens to individual atoms. But if you want to add hydrogens to all the atoms, you click add hydrogens and it gives you, it puts hydrogens on all the atoms that require calculated positions. And then we do a refine. Refine again. And we got it converged. Update our chemical formula. Now, if we go and look and see about the quality of the data, again, info, reflection statistics, I like the I sigma versus resolution. So here again, you'll notice that only the very, very high angle data was very weak. So again, some people normally cut off at 55, but even the data up to about 57 is still good. So whether you cut off 55 or 57, it's up to you. But I'll just, since we're being consistent with 55 with Molly radiation, again, 50 is the minimum cutoff. You can't go any lower than 50. But this is very good data out to about 58 degrees 2 theta. So again, to omit high angle data, we go to edit, edit instructions. In the second set of instructions, you'll just type omit -3, and then the 2 theta value you want to omit above. So omit -355, and now we can click refine. All right, now let's check to see if there's any bad reflections. So click on info, bad reflections. You'll see here there's one reflection where the error over ESD is greater than 10. So if we just click omit, it'll omit that reflection. So then we can click work, refine. So one thing I want to mention here is if we look at this structure, if you're looking at it, you may notice, for example, this atom here, this is a carbon atom, but it's very, very small thermal ellipsoid. Likewise, you'll see that when we did a calculate hydrogen atoms, it did not put any hydrogen atom on this position. And if there was no hydrogen atom placed on this calculated position, this may infer that maybe this is not a carbon. Because if this was an sp3 carbon, there should be a hydrogen atom that was produced. And maybe you say, well, it just didn't do it. Let me manually try it. So if I go to tools, and if you click on sp3 carbons for the first one, let's see if it'll put a hydrogen atom there. Oh, it did. Okay. Well, let's see what happens. And you'll notice that now we see these big electron density peaks surrounding this carbon position. Let me delete it one more time. Hit refine. Let me increase the peaks. You'll see where I'm going with this. 30. So what I want to show you is when I look at the 30 highest Q peaks in this structure, none of them correlate to a Q peak off of this carbon atom, the C009. So even though I place a hydrogen atom on a calculated position, the fact that there's no electron density off of this carbon atom to suggest a hydrogen atom is there, that's a good indication that this is the wrong atom type, because there's no electron density peak off of this carbon atom. Because if this was in fact a carbon atom, there would be an electron density peak about an angstrom off, roughly, that would suggest a hydrogen atom. But you see here, there's none. And if you want me to show you, let's say the carbon next to it, let's delete it, the hydrogen, and click refine. Notice here that there is a Q peak about, if you go to bang, it's about 0.978 angstroms. So there is a Q peak off of this carbon, but there is not a Q peak off of this carbon. So this would indicate to us that this cannot be a carbon atom, because there's no double bonds on any of these bonds shown here. Because this carbon cannot be a double bond here. This carbon cannot have a double bond here, and this carbon cannot have a double bond there either. So now I go back to tools. You can add a hydrogen atom. And then when I add that hydrogen atom back, you see it models that electron density like it should. So now what other atoms could it be? Most probably it's a nitrogen atom. Oxygen, it couldn't be because it'd be a trivalent oxygen atom. So let's change this to nitrogen. And nitrogen makes sense because if it's a 3-coordinate nitrogen atom, there would be no hydrogens off of that position. So we click refine. And you see now the thermal ellipsoid looks similar in size to its neighboring atom types. So now if we look at the other, any other atom positions, are there any thermal ellipsoids that don't look right? So we checked this one out. This one was correct. It's about 0.018, 0.012, 0.019. And so for now, if we want, well, this one here doesn't look that well compared to the other ones. If you want to confirm that this is a carbon or not, one thing to do is delete the hydrogen that we placed on calculated position, refine it, and see if a Q peak shows up off of that position. And so here there is a Q peak, but it's only about 0.5 angstroms away. So it's not really a Q peak related to a hydrogen atom. But again, the ellipsoid is quite small. So let's change this to a nitrogen atom. So now when we change this to a nitrogen atom, now we see another Q peak appear. And if we check the distance of this, it's about 0.85 angstroms from the nitrogen atom. And this would suggest that there's a hydrogen off of this nitrogen atom. Now, does that make sense that the hydrogen is off this nitrogen? Well, yes, because this nitrogen is only 2 bonds here, which are single bonds. So therefore, there must be a third bond, which is a hydrogen. So if you right click, type hydrogen, you can turn that into a hydrogen bond. And then we click refine. And you see, as we're making these changes, you see the R factor is slowly improving. So these are positive changes we're making to the structure. And then make sure, since it's a hydrogen placed on electron density peak, you got to right click UISO 1.2x. Refine that as well. Is that the 4 highest Q peaks that remain show up in this region here. And if we look at the Q peaks, or the atom sites here, you know, you look at the ellipsoids, look a little bit small compared to the neighboring ellipsoids. And there's also some unmodeled electron densities still about these 2 atomic positions. So again, if we think these are carbon atoms, let's delete these 2 hydrogen atoms and see if we see electron density peaks that correlate to those hydrogen atoms. If we hit a refine, and we look here, we see that there is no Q peak off of either of those carbon atoms. So this is a good indication that maybe, hey, these aren't carbon atoms. These might be something a little bit heavier. So now we have to use our chemical intuition and think of what else could these 2 positions be. And if we look at the bond distance between them, it's about 1.24, which is a double bond, you know, some type of double bond distance. And so if it's not carbon, well, obviously it can't be oxygen, because you can't have an oxygen-oxygen double bond in the middle of a molecule, at least not on normal conditions. So the only obvious candidate is maybe a nitrogen atom. So let's change these 2 to nitrogen atoms and see if that improves our model. Now again, when we do this, we shouldn't see any hydrogen atoms pop up off of the nitrogen, because this is a double bond nitrogen here. So it already has its 3 bonds. So there shouldn't be a hydrogen atom off of this. So if we hit refine, you'll notice now there's no hydrogen peak, or no Q peak resembling a hydrogen off of these nitrogen atoms. So sometimes the add hydrogen function can be misleading, especially if you have a atom type that is wrongly assigned as a carbon. It may think that should be a hydrogen there, because again, it uses calculation to determine that position. But upon further inspection from the electron density peaks, we see there's no hydrogen there, which will confirm that these 2 positions should be nitrogen atoms. And as you've noticed, as we kept improving the model, our R factor, which was at about 26, 28%, as we made these changes to the structure, now we're down to 18.6%. So we made good improvements to the structure. Click refine to get this to converge. You see most of the residual electron density shows up. It could be from the pi cloud and the aromatic rings. So there's not really any electron density left that would result in some type of atomic position. So we can go ahead and decrease the peaks, because all the remaining electron density is just residual electron density. So now we can start changing the weighting parameters. So I'm going to use the suggested weighting parameters provided by the OLEX. So I'll click on it. And if you're using OLEX.refine, I think you have to check on the box. And then you hit refine. This is a beautiful structure. We have 4.8% R1, WR2 is 11.2. Our goof is a little high. Let's use our second suggestion. Click on that again. Hit refine. So here the goof is a little high. So what we're going to do is we're going to go into edit instructions and we're going to increase the second weighting parameter to lower our goof. So we go to edit instructions, find the WGHT command line, the second number, increase it so that it lowers the goof. So I'm going to put about 1.1 for that value. Hit refine. It's better, but needs to be slightly bigger, or it needs to go a little bit lower. So I'm going to increase it from 1.1 to about 1.3. And this is just fine tuning the refinement parameters. So now everything is green. Green is good. We'll just do one last check of the info for bad reflections. So you see there's no remaining bad reflections listed in the in this HKL list. Now we go to report. Now, since this was collected using Chrysalis Pro, the newest version of Rigaku's software to run the diffractometer, most of this information about the absorption correction, diffraction, came from the sift.od file. And so you see most of the diffractometer was put in there, but for the diffraction temperature and cell measurement, this was 98 Kelvin. For the crystal, here we just, I believe if I go to the, 1 second, clear, dark, yellow, 0.2, or 0.2, 0.1, 0.05. And typically, when you do the finalizing of your data collection, you usually measure the crystal, and there you get the crystal dimensions. And this was mounted on a nylon loop. That's what so click refine. Now we're ready to do our check SIF and see if there's any errors we need to address. So we'll just look at a few things, make sure everything looks good. So there's no check SIF A or B errors. Only 2 C errors, not bad. One thing we did forget to do was the labeling. So I'll just show you that quickly when we get back to the OLEX window. It does suggest chirality, so you need to confirm the chirality of C00J, C00R. So as far as the structure model, we're finished. You know, there's no significant errors with the structure. So now let me shift back to OLEX. And again, to label the atoms, you go to mode naming and do this for each atom type. So we'll start O1, CL1, do the fluorines. Now for the nitrogens, I'm going to first do this ring here. So I'm going to start here, N1, N2, N3, N4. And then we do mode naming again for the carbons. So for carbons, C1, go around like this. And once you finish labeling, make sure that you refine it to update your CIF file. And if you wanted to, you could do another check CIF so that way it reflects the updated labeling as well. And then one last thing, if you want to do a picture of the asymmetric unit, you kind of, if you hold the left mouse key, you can rotate your structure. The right mouse key, you can zoom in and out. And we click on the drawing arrow. Again, if you want to change your labeling color, you click choose the label color. I like black, but the default is green, so it's up to you. Just go and change the ambient font to whichever color you like. Now, I recommend using the bitmap images. And if you want to change the font size, you can click, once you click on bitmap images at the bottom, you'll see label fonts, and you can change it to, font size 10, 12, 16, 20, 24. And then you go and you can click on either, if you only want a few atoms, you can select them and then click this button. It would only label those that were selected. If you just want the heteroatoms, you can just click that. If you just want non-hydrogen, it'll tell you all the labeling of the non-hydrogen atoms. Now, if you hold the shift button and the left mouse button, you can click and drag the labels. So that's pretty cool. And, you can kind of organize it the way you want. And then when you're ready, you just hit go, and it's going to create a JPEG of your structure. So again, these are the steps we do in solving a crystal structure. This one took a little bit long because I want to show you some of the troubleshooting that we use to help us when maybe we have a wrong atom type or other types of errors associated with the structure. So if you liked the video, hit the like button in the comment section. Thank you.